when we're dealing with work, work is often equated in English to effort. And that has absolutely nothing to do, because I can put it forth a lot of effort, I can use a lot of forces and still have no work being done. Work on its own is based on a calculus, vector calculus type definition. So it's actually really, really hard to put into words. The best I could do for a definition of work would basically be that work is the force, is the product of the force applied on an object in the direction of displacement and the displacement. So really kind of confusing right off the bat, and that's because it is a mathematical equation. It's actually based on a cross product in vector calculus. And we don't do vector calculus here in Physics 1, so we kind of have to come up with kind of simplified definitions of how the work equation is. If I wanted to put this equation into these words into equation format, I would say that the work is equal to F parallel times D, or work is equal to F times D parallel. So those are two different statements of the same thing. So what do I mean? Okay, well, what I mean is, let's say I take a box and I push it some displacement across the floor, and the force that I apply is directly to the right. Then, since my force and my displacement are parallel to each other, my work would just equal F times D. Okay, nice and simple. So if, though, I was to take that box and move it that same displacement D, but instead of pushing horizontally, I push straight down, or I just push down at an angle, then what's happening is not all of my force is in the direction of displacement. So if I were to resolve my force into a component that is parallel to the displacement and a force that is perpendicular to the displacement, so I can have an F parallel and an F perpendicular. If I was to calculate the work, that work would equal F parallel times displacement. And the perpendicular component there is not contributing to work. So if these were the same force of magnitude and all I did was change that angle, then the work that I do in this case is going to be larger than the work in this case, because F parallel here would be smaller than this F. So I can move the same displacement and apply the same force, but do a different amount of work. So the reason that I could do, like say this FD parallel instead, so let's say that I had a box that was sliding on a ramp, and it moves some distance D, and I wanted to say find the work done by gravity, I could do something like this and keep my axes the same here, and I could find the component of the distance. So let's actually define that distance here. And I could find the component of the displacement that is parallel to FG instead. So I could resolve my distance here, my displacement vector, into a D parallel and a D perpendicular. And only the component of that displacement that's parallel to FG here would do work. So the work done by gravity in this case would equal my FG times D parallel. Or I could take that same problem so let's take this same problem here. Let's kind of a different ramp angle. And move a displacement of D. And I can rotate my axes like I normally do on a ramp. And I would have my FG, and instead I could find the components of gravity that are perpendicular and parallel to my displacement. And the work done by gravity will equal FG parallel times D. And these will equal each other. So these two methods are equal. And there'll be problems in class where we can take a look and actually do those calculations to prove that they're equal. So the reason that this works is basically based on trig. That if you do F parallel D or FD parallel, this works because of kind of the trig relationships between this. Now on your AP formula sheet, they have an additional definition where they say work is equal to FD cosine theta. So they define it as FD cosine theta. Now I don't personally like this definition because this assumes that theta is the angle between F and the displacement vector. Okay, this only works if theta is that angle. So let's take a look at these two examples right here. So let's define theta as the angle of my ramp. So let's say that's the theta that's defined in my problem. They give me that angle. Now, when I'm looking at this example right here, that is the angle theta. So if I wanted to calculate FG parallel is FG sine theta. And then you're like, whoa, 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 it's supposed to be a cosine theta here. Well, it's not in this case because this angle theta is not the angle between FG and my displacement. That's actually this angle right here, which is a different angle. So this FG sine theta would not be the same as this angle theta here. Now, if I take a look at this same triangle, this is my angle theta. If I look at the triangle right here, that's the same as this angle theta. So if I was to define D parallel here, D parallel would be the opposite side of that, so that would be D times sine theta. So if I were to sub in those two equations here, I would get FG parallel as FG sine theta times D, and over here I would get FG times D sine theta. And then these two statements are equivalent. So these are equivalent definitions of work, but they don't match this equation that's on the formula sheet. And that's because the angle they defined here is theta, whereas this theta is not that theta. This theta is basically 90 minus the theta that's here in this diagram. So that's why I don't like this equation, because this one only works if they actually give you the angle between force and displacement. So the angle theta that is in this equation is this particular angle here. It has to be the angle between those two vectors when they are in contact with here at the point of that angle. So we can do kind of work calculations based on that. Now, work is going to be very, very, very related to energy and how we change in speeds and kinematic variables. There's so many different things we can pull in with work. So there's one more thing we kind of have to talk about work, and that is work is actually a scalar value. And it's a scalar because even though it's the product of two vectors, the result only has a magnitude. But work can be positive or negative. But those positive and negatives are not direction. So if we take a look at just the equation, work equals F d cosine theta, if I was to have my force here, F, and I was to have my, let's just say my displacement was in the exact same direction. If I was to calculate this, the theta here in this example would be 0 degrees because they are in the exact same direction. So the cosine of 0 is 1, so the work here would just be F times d. Okay, well, what if instead I kept my force in the same, let's just keep the displacement in the same direction because that's easier for my brain. So my displacement's in the same direction, but now I'm pushing at an angle. So in this case, theta is going to be greater than 0, but below 90. And my cosine theta is positive. If you were to calculate cosine of any value between 0 and 90, your cosine theta is positive. So the work done will be positive. Because here we're just looking at magnitudes. When you do this, this is just the magnitudes of those. We're using the cosine theta to take care of direction. Now, if we were to look at another example, so if I had my displacement here, but then my force was perpendicular, if I were to look at that example, then theta would be 90 degrees, and the cosine of 90 is 0, so my work would be 0. So there would be no work at that point in time. So this motion, if this object was moving, but the force I'm analyzing is perpendicular to it, then that would do no work. So imagine a box sliding on the ground. The normal force is perpendicular to the displacement. The normal force wouldn't do any work. Now, we can also go back and then take a look at some other angles. What happens if my displacement is this direction, but my force is acting in the opposite direction? For example, friction. Kinetic friction works in the opposite direction of the displacement. Well, in this case, theta would be 180 degrees. So cosine of 180 is -1. So my work would equal a negative F times d. So I get a positive FD when they're parallel, and I get a negative FD when they're anti-parallel. So I could also have other circumstances here. I could have D, and then I could be at some other angle. And there's my angle theta there in that case. So if 90 degrees between theta and 180 degrees, then our cosine is going to be negative, and our work is also going to be negative. So essentially, I get positive work if my force is working with the displacement. If my force has at least some component that is in the same direction as displacement, that's going to cause a positive work. And that positive work is going to mean that my objects are going to have a tendency to speed up due to that force. That force is working with the displacement. So a positive work means that you have at least some component parallel to the displacement. And that's going to have a tendency to cause objects to speed up. We'll see why when we talk about energy. And if we have negative work, then that means that at least some component of the force is anti-parallel to the displacement. And that's going to have a tendency to want to cause objects to slow down. So even though work is positive or negative, the work does not have a direction. I cannot draw a vector for work on this diagram, but the directions of my vectors help determine whether I have positive work or negative work. And once again, the sign of work will start to make a little bit more sense when we start talking about changes in energy. And so you can see we can relate to like changes in speed and so forth here. We can define net work as the sum of the work done by all forces. Acting on an object. And once again, this is a scalar value. So it can be positive or negative, but we're going to have, it's going to be a scalar.